Hello everyone, it's Miss Maneely, and I am going to do our second tutorial for the marking period review for Algebra 1 on quadratic functions. And if you look at the section in your quarterly review packet on quadratic functions, you'll see that some of the questions specifically say to complete the problem without a calculator. And that's because on the quarterly assessment there are two sections. One of the sections is to be done without a calculator, and one of the sections is to be done with a calculator. And so you will see throughout your review packet that there are problems where you are not supposed to use a calculator. So I want to reinforce that in the review. Let's take a look at problem number 6. It says for a given quadratic function, negative 3i is a root. Well, negative 3i is an imaginary number. And one of the things you need to remember about imaginary numbers and complex numbers is that when they represent the root of a polynomial, whether it's quadratic, cubic, quartic, whatever, that all of your complex roots are going to come in pairs. And the pair is going to be your complex conjugate. So if you remember, a complex number has two parts. It has a real part, let's call that A, and an imaginary part, where you have B times your imaginary unit I. So that is a complex number. The complex conjugate of that number would be A minus BI. Notice that the real part stays the same, but the imaginary part switches signs. So if I'm told that a quadratic function has negative 3i as a root, that must mean that positive 3i is the other root. And then in letter B, it says to assume the leading coefficient is 1. And it says to write the equation for the quadratic function in factored form. So remember, standard form is when it's of this form, ax squared plus bx plus c. And factored form, or intercept form, is going to look like a times the quantity x minus p times x minus q, where p and q are your roots. So notice that when you write them in the factored form, you have to switch the sign when you put the number inside the parentheses. So for example, I know that a, I'm told, is 1. So when I write my equation, I know that a is 1. And then I'm going to write my factors, right? And it's going to be x minus, and then I'm going to enter in the actual values. So if 3i is one of my roots, I can go ahead and write that there. And if negative 3i is the other, it's going to look like this. But what happens when you subtract a negative number? This ultimately becomes a plus. So ultimately, if you write it in, if you simplify this expression, it's going to be that y is equal to x minus 3i times the quantity x plus 3i. And that's all you would have to write in this section. So this is your equation in factored form. In letter C, it says to use the factors in part B to write the function in standard form. Well, standard form, all we're doing is simplifying the expression. And if I'm multiplying these two factors together, I just need to distribute all the terms in one factor to all the terms in the other. And there's two ways you can do this. Most of you are familiar with foiling. So if we have y equals x minus 3i times x plus 3i, foiling stands for multiplying the first terms together. That would be your x's. And so if I multiply them together, I get x squared. The O stands for multiplying your outer terms, so that would be x times 3i. That's going to give you a positive 3i times x. The I stands for multiplying your inner terms, so that's going to be a negative 3i times x, or simply a negative 3i x. And then the L, that stands for multiplying the last terms in each of the parentheses. Negative 3i times positive 3i. So if you multiply the coefficients, you're going to get a negative 9. When you multiply your i's together, remember that's going to give you an I squared. When you start to simplify, you should hopefully notice that your 3ix and negative 3ix are going to cancel. The other thing you have to remember when you're simplifying this expression is that I squared is not imaginary. I squared is going to be the square root of negative 1 squared. And when you simplify that, the square and the square root are going to cancel each other. And so it turns out that I squared is just the real number, negative 1. So when I simplify this expression, I'm going to bring down my x squared. But my negative 9 times I squared becomes minus 9 times negative 1. And that, when I simplify it, is simply going to be x squared plus 9. If you prefer to use the box method, which is totally fine, you're still foiling, which is, again, just the distributive property. It doesn't matter the order that you write your factors. So, for example, I could do my x and my negative 3i on the top, and I could do my x plus 3i on the side. And notice in this first box, when I multiply my x's, I get that x squared. That just corresponds to the f and FOIL. I multiplied my first terms. When I distribute the x to the negative 3i and get negative 3ix, isn't that what I got here? And when I multiply the 3i times the positive x, I get a positive 3ix, which is really what I got right there. And then my positive 3i times negative 3i gives me my negative 9i squared, which is what I had here. So it doesn't matter if you use the FOIL method or the box method. You're ultimately distributing each of the terms in the first quantity to each of the terms in the second quantity. And it doesn't matter which way you do it. You just want to make sure that everything gets matched up. Ultimately, if you're using the box method, you want to combine your like terms just like we did with FOIL, and our positive and negative 3ix's are going to cancel. Our negative 9i squared is just negative 9 times negative 1, which is positive 9. And when you add what's left over, you get that x squared plus 9 is going to be y. And that's our equation in standard form. In number 7, you are simply asked to perform the operations without a calculator. Be very, very careful of the operation listed between the parentheses. On the quiz or on the test that I had with quadratic functions, this was a common mistake for some of my students, where every time they saw the parentheses, they thought they had to multiply. So I had a lot of students foiling and using the box method when all they had to do was add or subtract like terms. So when you take a look at example A, those parentheses are just separating the two complex numbers. I've got 2 minus 3i plus a negative 1 plus 5i. Those parentheses do nothing but group the two complex numbers together. All I need to do to simplify this is to combine my like terms. And since everything is addition, I could actually rewrite this as 2 plus a negative 3i plus a negative 1 plus 5i. And notice how now everything's written in addition. So if I combine my like terms, I'm going to combine my real numbers. 2 plus negative 1 is 1. And if I combine my imaginary numbers, I've got a negative 3i and a positive 5i, which is going to give me plus 2i. Now, you don't have to remove the parentheses like that, but I just kind of wanted to show you that they really aren't anything but grouping symbols. They don't always indicate multiplication. In letter B, again, we're subtracting, or we've got the two complex numbers, and this time we're subtracting. The one thing you do have to remember with subtraction is that we're subtracting both of the terms in the second set of parentheses, which means that you have to distribute that minus. If you think about what this is, it's basically taking the quantity 7 plus 5i and subtracting the quantity negative 3 minus 2i. And if I'm subtracting each of those terms, it's the same as adding the opposite. So one of the things that I usually do is I change my subtraction to a positive, and then I change, sorry, my board is not calibrated anymore. Let's try this again. So if I've got minus and I'm subtracting that whole quantity, it's the same as adding the opposite. So if I change my subtraction to addition, I want to make sure that I change the sign of each of the terms inside. And so ultimately, I'm just adding. So I want to add my like terms. So I'm going to add the 7. This is now a positive 3, which gives me 10. And then I have a positive 5i and a positive 2i. When I combine them, I'm going to get a positive 7i. Now when I get to C and D, I am multiplying. And so in letter C, I'm multiplying two complex numbers. And again, you can use the FOIL method or the box method. It doesn't matter. I'm going to go ahead and use the FOIL method for part C. So when I use FOIL, that means I'm going to distribute the 2 to the 3. And I'm multiplying now. So I am going to do 2 times 3, and that's going to give me 6. I'm going to multiply 2 times 2i, and that's going to give me plus 4i. And then I'm going to distribute the negative 6i. So make sure you distribute the negative along with it. Negative 6i times 3 is going to give me a negative 18i. And negative 6i times a positive 2i is going to give me a negative 12i squared. Now this time my middle terms don't cancel. That's only going to happen when you're multiplying complex conjugates. If you're just multiplying two complex numbers, your answer is still going to be complex. So when I simplify, I know that these two middle terms, I can combine them since they're both imaginary numbers. I've got a 4i and a negative 18i, which is going to combine to give me a negative 14i. The other thing I want to notice is this expression right here. Remember, I squared is a real number. It's negative 1. So this quantity is just negative 12 times negative 1, or positive 12. And that means that I can combine my 12 and my 6 together to get 18. And so when I multiply two complex numbers, as long as they are not conjugates, I should get another complex number. Let's take a look at the last one. I'm looking at the complex number 1 minus 5i, and I'm squaring it. It is very, very tempting to distribute that power of 2 to each of the terms, but that would be incorrect. You need to remember that when you're squaring a quantity, it's the same thing as multiplying that quantity times itself. Now pay attention here. These two complex numbers are the same. They are not conjugates of each other. So when I multiply them, I should end up with another complex number. If the complex numbers were conjugates, I would end up with a real number, like we saw in number 6. All right, so this time I'll go ahead and use the box method. So I have 1 minus 5i and 1 minus 5i. And then let's go ahead and fill things in. I know 1 times 1 is 1. 1 times negative 5i is going to give me negative 5i. Negative 5i times 1 is going to give me negative 5i. And negative 5i times negative 5i is actually going to give me a positive 25i squared. And remember, I squared is just negative 1, so that's going to be 25 times negative 1, or simply negative 25. And now I want to combine my like terms. So let's combine the real numbers first. The real numbers are 1 and negative 25. That's going to give me negative 24. The next thing I want to do is combine my imaginary parts. I've got negative 5i and negative 5i. These do not cancel. They would only cancel if one was positive and one was negative. So this leaves me with a negative 10i. So notice that my answer is still complex. All right, let's take a look at number 8. This is a multiple response problem, or this was a multiple response problem on your unit test. And all you really need to do is identify the solutions that are real. You don't actually have to go through and solve each of the equations, although that's probably a good strategy for figuring out which are going to have real solutions. So if I take a look at letter A, I can see that I have an x squared term, a term involving x, and a constant. That means that I can write the equation in standard form. And when I do, that essentially means I'm going to add the 4 to both sides. And I end up with x squared plus 8x plus 4 is equal to 0. And one of the strategies you might try when solving would be to factor. And so I'd be looking at factors of 4. I usually do a factor table like this, where I take a look at my factors of 4 that add up to give you 8. And there aren't any. So in this situation, this is actually not factorable. So there are two strategies that you can use. One would be just to go ahead and start calculating the discriminant or using the quadratic formula to solve. And that's what I'm going to do because I feel like it makes a little bit more sense. The quadratic formula, remember, is going to be negative b, or the opposite of your b value, plus or minus the square root of b squared minus 4ac. All of that is going to be over 2a. So let's go ahead and fill in what we know. In my equation, a is 1, b is 8, and c is 4. So if I start solving this, I'm going to put my 8 in where the b is. So that's going to be the opposite of 8, or negative 8, plus or minus the square root. I'm going to have 8 squared minus 4 times the value of a times the value of c, that's also 4, all over 2 times 1. And so when I start to simplify, I need to simplify what's underneath my square root. So I know that 8 squared is 64. So this is basically going to be the square root. Let me include my 8 in there. So when I simplify, I'm going to have negative 8 plus or minus. This is going to be the square root of 64, and then negative 4 times 1 is negative 4. When I multiply that times 4, I'm going to get minus 16. And all of that is going to go over 1. So you don't actually have to go any further than this. One of the things I know is that 64 minus 16 is a positive number. And if I try to take the square root of a positive number, I'm going to get 2 real roots. That positive number underneath the square root is called your discriminant. So when that number is positive, we know we have two real roots. If that number is negative, that would be an indication that we have two complex or imaginary roots. And if that number is 0, well, the square root of 0 is just 0. And it wouldn't matter if I added that or subtracted that from -8, I would get the same answer either time. So when your discriminant is 0, we have one real root, and it happens to be a double root, as we saw with polynomials. So because I know that my answer is going to be real, I can go ahead. It says to put a star. Now, actually, in this problem, it does say to go ahead and determine the zeros without a calculator. So let's go ahead and finish solving. 64 minus 16. 64 minus 16, because it says to do this without a calculator. So if I borrow 1 from the 6, I get 14 minus 6. It's going to be 8, and then 5 minus 1 is going to be 4. So I'm left with -8 plus or minus the square root of 48 over 2. And one of the things that I know is that 16 goes into 48 3 times. So I can actually rewrite 48 as 16 times 3. And since both of those are under the square root, this becomes -8 plus or minus. If I simplify the square root of 16, I get 4. I can't really do anything with the square root of 3, so I'm going to leave that there. And then that's over 2. And since both 8 and 4 are divisible by 2, I can reduce this a little bit further. That's going to end up being a -4 plus or minus. And all I'm doing is distributing the 2. So 2 goes into 8 -4 times, or 2 goes into -8 -4 times. 2 goes into 4 twice, and it doesn't do anything to that square root of 3. So this would be your final answer. In letter B, you'll notice that there's only one expression that involves an x, and it happens to be an x squared, and that means that you can actually isolate it and then use square roots to solve. So let's go ahead and get x squared by itself. If I add 25 to both sides, I'm going to have that 25 is equal to 4x squared. I still have to get x squared by itself, so I'm going to divide both sides by 4, and I'm ultimately going to have x squared is equal to 25/4. To solve this equation, I'm going to take the square root of both sides. And when I do, I have to remember that there's going to be two roots. So I'm going to include a plus or minus symbol. So that means that x is going to equal plus or minus the square root of 25 over 4. Well, I can split the square root up and take the square root of 25, which is 5, and divide that by the square root of 4, which is 2. And both of those numbers are also real. So I'm going to put a star next to that number. In letter C, I have a similar situation where I have one expression involving x. It's the x minus 2, the quantity squared, which means that I can get that by itself by subtracting 5. And so if I do that, I'm going to have x minus 2, the quantity squared, is equal to -25. And if I want to undo that power of 2, I'm going to take the square root of both sides, just like I did in the previous problem. And I have to remember when I do that, I'm going to have two roots, so I want to include the plus or minus. The square and the square root are going to undo each other, so I'm going to be left with x minus 2. And that's going to be equal to plus or minus the square root of -25. As soon as you see that negative, that should be an indication that we have an imaginary root here. So I'm going to basically rewrite -25 as 25 times -1. The square root of 25 is 5. And that square root of -1 is what we defined to be I. My final step in solving for x would simply be to add 2 to both sides. So in this problem, x would equal 2 plus or minus 5i. So I've solved the equation, and I've learned that my solution, or my root, is not real. So I'm not going to put a star next to this problem. Letter D is the easiest of all because you're given a graph and you can actually see the x-intercepts on the graph. That means that this function has two real roots at -1 and or +3. And both of these are real numbers, so I'm going to put a star next to it. If I had a situation where the graph didn't cross the x-axis, I wouldn't be able to state the roots because they would be imaginary, and I wouldn't be able to do any algebra to figure them out. So unless you could somehow model the equation. So if your graph did not hit the x-axis, all you'd be able to say is that there are imaginary or complex roots. You wouldn't necessarily be able to identify exactly what they are. In letter E, this is also a nice kind of an equation to solve because the equation is already in factored form and it's set equal to 0. And we have a property that says if I multiply a bunch of things together and my answer is 0, then one of those things has to be 0. So if I'm multiplying the quantity 2x plus 1 times the quantity x minus 3, and the product is 0, then either 2x plus 1 is equal to 0, or x minus 3 is equal to 0. That's the only way this can happen, is if one of those terms is 0. And so what I'm going to do is I'm going to solve each one individually. So for the first one, I'm going to subtract 1, and we get 2x is equal to negative 1. If I divide by 2, I get that x is equal to negative 1/2. Most of you at this point are able to examine the next one, x minus 3 equals 0, and know that the root is going to be at positive 3. And if you don't know that, you can simply add 3 to both sides, because that's the inverse of subtraction, and we'll learn that x is equal to 3. Both of those are real roots, so again, I'm going to put a star next to that problem. Okay, in problem number 9, you're given some data. It says, for the past 6 months, Miss McNeely has noted the cost of her electric bill, and the data is shown in the table below. So you can see I've got data for February, March, April, May, and June, and July, and the electric bill for each of those months. You're told to let T equal 1 correspond to January, and T equals 6 correspond to June. Because if I think about trying to enter this data into my calculator, I can't enter those months into a list. So I have to somehow rewrite them so that they are numeric. So it says to let 1 correspond to January. So that must mean, and what I'm going to do is I'm actually going to create another column in my table, and I'm going to call it T for time, or time since January, I guess. Oops, let me fix that. I didn't mean to do it that way. Okay, so if January corresponds to T equals 1, that means February must be 2, March must be 3, April must be 4, May must be 5, June is 6, and July is 7. And I just want to double check that T equals 6 corresponds to June, and that is true, so I know that I have assigned my values of T to the months correctly. And it says to determine a quadratic regression equation to predict the cost of the electric bill from the month. And it says to round to 3 decimal places. So because it tells me specifically to do quadratic regression, I need to enter this data into my calculator. So I'm going to go ahead and in my list, so if you hit stat and then enter, what we want to do is go into our list and enter the data. So let's go ahead and do that together. So in list 1, again, I'm not entering in February, March, April, or May. I'm entering in the values of T. And be careful, because February is the month I'm starting with, and that's going to correspond to T equals 2. And we're going to go all the way to July, which is T equals 7. And then in list 2, I'm going to enter in the cost of the electric bill. So in February, my bill was $125.95. And then in March, it was $106.60. And then in April, it was only 68 bucks. I was really cutting back. And then in May, it was $59.71. In June, it was only $45.71. And in July, it was $64.21. Okay. So you're asked to come up with the quadratic regression equation. So I'm going to go to my home screen. I'm just going to hit second quit. To come up with the regression equation, again, we've just entered statistics into our calculator. And so I'm going to go back to my stat menu by hitting the statistics button. But instead of entering the data, I want to calculate something. So I'm going to use my right arrow and scoot to calc. And this gives me a list of all of the different possible regression models that your calculator can determine. And I want to do quadratic regression, and so that's the quad reg option, which is number 5. So choose number 5, and then tell your calculator where everything is. So for example, my x's are in list 1, my y's are in list 2, and if that's different, you want to make sure you change it. And you can change it. So let's say that this said something else. If I wanted to put a list 2 here, I'm going to hit my second button and then 2, which is how I would enter in list 2. Another thing that you can do is store your regression equation. And for this problem, you ultimately don't have to, but I will show you a shortcut. So what I'd like to do is be able to send my regression equation into my y equals screen so that I don't have to type it in and avoid rounding errors. because I want to type it into y equals, y is a variable. So I'm going to hit my vars button. I'm going to scoot over to where it says y variable, or y vars. It's a function, so I'm going to press enter. And then notice that you're given the list of all the possible y equations in your y equals screen. So I'm just going to choose y1. And I'm going to scoot down to calculate and press enter. And so you'll get your regression equation. Now please note in the instructions it says to round to 3 decimal places. This is very important on the quarterly assessment, and you will be docked points if you don't round correctly. So please, please, please be mindful of rounding. So my equation is in standard form where we have y equals ax squared plus bx plus c. So y is going to equal, I'm going to replace my a with a 5.136, and if I look at the next number, that's also a 6, which means that I'm going to need to round up. So it's going to be 5.137, and then make sure you put your x squared there, because a lot of people sometimes forget to write their x's in the equation. My b value is negative 60.505. Since the next number after that is a 4, I don't need to round up, so I'm going to leave it at that. So I'm going to have minus 60.505. And again, put your x. And then finally, my last term is c, which is 231.639. Since the next number is an 8, I would need to round the 9 up to a 10, or the 39 up to 40. So this is actually going to be 231.640. Now, I did realize that the problem is telling me to let t represent time, and in my equation, I wrote the letter x. So to be consistent, I'm going to go back and just call that t. It doesn't matter what you call it, but you should be consistent. If the problem is telling you to use a t, then use a t. Okay, and so in this case, t represents the number of months since January. Oops, I spelled months wrong. Don't usually do that. And I'm letting y equal the electric bill. Okay. It says in letter B to use your model to predict the cost of Miss Manili's electric bill in April. So again, I can't just plug the word April into my equation. I somehow have to quantify April. And if I look in my table, I can see that April corresponds to the 4th month. So I'm going to let t equal 4, and I'm going to plug it into my equation. So if you're going to do this by hand, you should write it out. So 5.137 times 4 squared minus 60.505 times 4 plus 231.64. And then you can just type this into your home screen. So I have 5.137 times 4 squared. And notice that I'm putting it in parentheses. It's important that you do that in case you have a negative number, because if you try to square a negative number without using parentheses, your answer is going to end up being negative when it should actually be positive. So just get in the habit of putting parentheses around the numbers when you are using the substitution method, or when you're substituting. Okay. And so my predicted bill for April, according to my model, would be $71. And if I rounded that, that would be 81 cents. That would be my predicted electric bill. And so if I look at April, I can see that the actual, so this is the actual bill. My actual bill was $68. My equation provides a prediction. And what you are asked to do in letter C is to calculate the residual for April's bill. The residual is just that difference between the actual and the predicted. Now I will say on the quarterly assessment, you will not be given the equation. So you have to know what a residual is. And it's always starting with the actual value from either a table or a graph. So if you're given a graph, you just go into the graph and look up where t is equal to 4. Figure out what the actual value is. And then the residual is just the difference. So I'm going to take 68 minus what I predicted, which is 71.81. And so if I do 68 minus 71.81, I get negative $3.81. And that's in dollars. And so if I ask, is that an over prediction or an under prediction, or like did my model overestimate or underestimate? Well, I can see really clearly that my prediction was higher than the value in the table. So notice that when your prediction is higher, your residual is actually going to be negative. And that's because the prediction's higher. So it's overestimating what the actual cost is. And if you look, that's not a huge difference when we're talking about the cost of electric bills. Being within $4 isn't too bad. So it's a pretty good fit, I think. And if I wanted to know for sure, I could go back to my scatter plot. So if I wanted to set up a scatter plot, I would just go into second stat plot. I'd want to make sure that I was using the correct list 1 and list 2. And then I'd hit zoom 9. And so you can see, because I sent the regression equation to y equals, you can see very clearly my model fits the data fairly well. And then once I have it graphed, I can find things like the minimum. I can find where it intersects different values, but we'll save that for a different problem. All right, so the next section has to do with polynomials, and I'm going to save that for another video. So check back for video number 3 on polynomial functions for the review for your Quarter 1 assessment.